Let us look at the various components that are present in the biogeochemical cycle. We will be looking at the solutes that are present in glacial runoff and their sources. The first one is the atmosphere. The atmosphere has sea salt, acidic nitrate and sulfate aerosols temporarily stored in snowpacks and ice, and gases such as CO2 and oxygen. And when we talk about the chemical weathering of rocks, the base cations calcium 2+, magnesium 2+, sodium plus and potassium plus, and dissolved anions such as bicarbonate and sulfates. These are the solutes that are present in the glacial runoff. The main source of chloride to runoff is snowmelt, but there may be a difference in the chloride concentration due to location of snow. That means continental lower area versus coastal higher areas. In the continental area, we will have lower concentration, and in the coastal area, we will have higher concentration of chloride ions. Both bicarbonate and sulfate concentrations are highest during the early snow melt season. Let us look at chemical weathering of minerals. Most of the iron found in the mineral waters apart from the early snow melt are derived from the chemical weathering of minerals. The magnitude and rate of solute acquisition from chemical weathering is usually dependent on 4 first order variables. They are reactive mineralogy, reactive surface area to water ratio, duration of rock and water contact, availability of other species involved in the chemical weathering reactions such as protons and oxygens. So let us look at what are the geochemically reactive minerals. The geochemically reactive minerals in the order of decreasing reactivity are evaporites, that is halides and gypsum, carbonates, dolomite and calcites, sulfides, pyrites, aluminosilicates, example feldspar. Of these, evaporites, carbonates and sulfates have the dominant control in water chemistry. The variables that affect the hydrological drainage system include increasing the reactive surface area to water ratio increases the amount of solute in the solution per unit time. That means more interaction means more dissolution. This can be understood in that way. The reactive surface area to water ratio depends on the suspended sediment concentration, the particle size distribution. In other words, bigger particle will have more contact time, the presence or absence of microparticles, the size distribution and concentration of debris, for example, unfrozen subglacial debris through which water may be flowing. All these things affect the surface area to water ratio. So what are the variables that affect the hydrological drainage system? The increasing the rock water contact time results in increasing solute concentrations, although this increase with time is often non-linear. That may be sometimes it may be higher in the beginning, then later on it may reduce, or it may be the other way around. The rock to water contact time is a function of the residence time of water in a particular flow path or reservoir, and the availability of the limiting species such as protons, oxygen or carbon dioxide depends on factors such as proximity to the gas source and turbulence. The gas sources may be atmosphere or gas bubbles in the ice. The simple dissolution reactions such as the dissolution of halite or sea salt do not involve the consumption of other dissolved species. But the dissolution of rock floor normally involves surface exchange, carbonation and oxidation reactions which consume protons, dissolved carbon dioxide and oxygen respectively. So what is chemical weathering of carbonates? Chemical weathering of carbonate refers to breakdown or alteration of carbon minerals, mainly calcium carbonate, that is calcite, and dolomite, that is calcium magnesium carbonates, through chemical reactions typically involving water, acids and gases in the atmosphere. So this process is an important aspect of rock weathering and contributes significantly to the formation of soil and the carbon cycle. Let us look at the various aspects and their details. What are the primary process that is happening in the chemical weathering? The first one is carbonic acid dissolution, which is enhanced by acid rain and snow melt. Let us look at the chemical reaction that is happening. This is dissolution of calcite into calcium bicarbonate. So how does this happen? Carbon dioxide in the atmosphere gets dissolved in water to give carbonic acid. This carbonic acid reacts with calcium carbonate to produce calcium bicarbonate. So what are the environmental factors that are involved in the weathering process? Cold temperatures, low precipitation, seasonal thaw, permafrost and ice cover slow down the weathering rates. That means at low temperature the reactions are slower. And what are the other influencing factors? Acid rain, climate change, thawing, permafrost and seasonal meltwater contribute to increased weathering during warmer month. And what are the impacts? This contributes to the carbon cycle and climate regulation. This also shapes the Arctic landforms. It influences the ecosystem, that is soil and water pHs are affected. So what is the significance of chemical weathering? The chemical weathering of carbonate contributes to carbon sequestration. It also affects landscape formation and it impacts Arctic ecosystems. So there are two major systems. One is the distributed system, another one is quick flow waters. So we will look at how the weathering happens in these two different systems. What is the dominant weathering process that is occurring in the distributed system? Here, oxidation of sulfide minerals, that is protons derived from the oxidation happens. And in the case of quick flow waters, carbonation of carbonates is the major dominant weathering process. And what are the timing of this process? In the distributed system, the weathering process peaks early in the ablation season and remains constant thereafter. But in the quick flow waters, it increases throughout the ablation season. And what are the key factors that are involved in the distributed system? There is a reduction in areal extent of the distributed system and also the proportion of delayed flow waters in bulk discharge. These are all happening in the distributed system. And when we talk about the quick flow waters, there is a growth of channelized drainage system that is happening, and also there is an increase in the proportion of quick flow waters and the suspended sediment concentrations in the runoff that is happening. What is the source for the proton contribution? In the case of distributed system, the proton are derived from the oxidation of sulfide minerals. In the case of quick flow waters, it is not known, but carbonation dominates in quick flow conditions. And what happens to the weathering? This peaks early and then stabilizes in the distributed system. The weathering process peaks early but stabilizes later on. Whereas in the quick flow waters, it increases as the channelized drainage system grows. And what is the relationship between sediment with respect to weathering? We don't know in the case of distributed system, but in the quick flow waters, carbonation of the aluminosilicates fraction of the suspended sediment load increases. And what is the proportion of bicarbonates and cations? In the distributed system, it is not known, but in the case of quick flow waters, increase in atmospheric bicarbonate from carbonation of aluminosilicate happens. Also, there is an increase in the sodium and potassium ions from carbonation of aluminosilicates. And what are the factors that affect chemical weathering in glacial environments? The efficacy of the chemical weathering in glacial environment is due to the high flushing rates, which ensures that dilute meltwater do not reach chemical equilibrium with available sediment and the reaction rate remains very high. In the turbulent meltwaters, there is a transport of large quantities of fine freshly ground chemicals. Reactive rock floor happens. And in the case of high suspended sediment concentration, it increases with the meltwater discharge, which leads to increase in the flux of reaction rates. The low buffering capacity of the dilute meltwaters. When such waters come in contact with a large amount of reactive materials, the available protons are consumed more rapidly than they can be replaced by diffusion of carbon dioxide into solution, which results in change of pH, that is increase of pH, that is the concentration of CO2 decreases and CO2 to diffuse into solution also changes. So what are the various mineral weathering reactions? When water first infiltrates the land surface, microorganisms in the soil have a significant effect on the evolution of water chemistry. The organic matter in the soil is degraded by microbes, producing high concentration of dissolved carbon dioxide. This process lowers the pH because this increases in the carbonic acid in the water, so that leads to lowering of pH, and this also affects the soil water. The production of carbonic acid starts a number of mineral weathering reactions which results in bicarbonate commonly being the most abundant anion in the water. So that means more dissolution of carbon dioxide leads to production of more bicarbonate ions. When the contact time between the water and the mineral is shallow, groundwater flow path are short, the dissolved solid concentration in the water generally is also low.